All right, we're going to explore an interesting data type called a NetCDF file. And the source of the file that we're going to look at is going to be coming from NASA Goddard Institute for Space Study. This is the GIST surface temperature analysis that you'll often see in maps. So these are graphs here of the average of how the world is warming up over time. But this is just a line plot. This is actually a gridded data set that you can see here. This is a grid of what that anomaly looks like. It's not just the same everywhere on the planet. Some places are getting warmer a lot more than others. And so what we can do with that data is actually load it. It's a gridded data set, which means that you have in this case, we're going to come down here. It's a 2x2 grid all over the globe, which is found here. Compressed NetCDF files, regular 2 degree by 2 degree grid. So that's 2 degree latitude by 2 degree longitude. That's how big the grids are, with a land ocean temperature index. So this is with 1200 kilometer smoothing. So if you download this thing, you're going to get gzipped NC file. And so you should have a native compressor on your machine that will unzip this thing and turn it into just a regular .nc file. Now, a .nc file, what that stands for, a NetCDF. So what is a NetCDF? A NetCDF is a set of software libraries and self-describing machine-independent data formats that support the creation, access, and sharing of array-oriented scientific data. So this is for data sets that will have a latitude, a longitude, and a time or a depth dimension. So it's like a big cube of data that we're going to be looking at. So you can imagine the top layer being like the surface. It would be like the surface layer of the map. At time 1, maybe it's the globe, in a map, latitude and longitude. At the surface would be time 1. The next layer down would be time 2. The next layer down would be time 3. So it's a big giant cube. So interacting with these data, if you're going to be in meteorology and oceanography or GIS or climate studies, is pretty important. So we went ahead and downloaded one, and we're going to go ahead and load that into R now. I'm going to load it into R. So I'm going to start a new script here, where this is just going to be an overview, quick overview of CDF files using NASA GIS. Okay. All right. So I'm going to go ahead and set my working directory. Tools. Let's see. Session, set working directory, choose a directory. Okay. I'll go ahead and just paste that up in here. Set my directory. And then I'm going to require 2 really critical libraries. Fields, and NetCDF4. And you can install these if you go to Tools, Install Packages. You can type Fields and NetCDF4 and go ahead and install dependencies and hit Install, and you should be good to go. So we're going to load these things. Once you have those libraries loaded, NetCDF file is a little different. You don't just open the file and have it dump all the data to your program. What you do is you open a connection to the file using a function called nc_open, which then opens sort of a pipeline into the file. Then you request something from the file. And you might say, well, how do I know what's in there? Well, you're going to use this function called nc_open, and you should have a file that looks something like this. It's .nc file. And we're going to open a connection to it. And then when we type F, this is a description of the connection. So there's 2 variables inside of here. There is an integer, which are the time bands. We're not going to worry about that right now. But then there's something called short, which is the temperature anomaly. This is the surface temperature anomaly. The units are in Kelvin, which is really similar to Celsius. It's Celsius plus 273. And there's the fill value, And there are 4 dimensions to this. 1 dimension is latitude, 1 dimension is longitude, 1 dimension is time, and 1 is NV. We're not going to worry about that right now. Our temp anomaly has 3 dimensions: longitude, latitude, and time. And so here they are down here. Latitude is size 90, that's how long it is. Longitude is size 180, and time is 1,669. That's how many times there are, and you can see that it's days since 1800-01-01. That's how far back this anomaly goes. So we can request a couple things out of this file now. Let's go ahead and request latitude. We'll just call it lat. We'll use a function called ncvar_get. We're going to get a variable out of this file. We're going to put our connection in here so that R knows we're getting this connect. We're going to look in this connection for something called lat. And here's lat right here. And so when we request this thing, here is lat, there's our latitudes for this file. And we can do the same thing for longitude. Oops. Longitude. Here's our longitudes for the file, okay? And then what do we do with time? Let's just call this TM. We're going to do something really similar. From our connection, we're going to get something called time. Now, when you look at time, you'll see that time doesn't look like a time. Because if we remember, in our connection to the file here, it says that the units are days since 1800, January 1, 1800. So this is the number of days since January 1, 1800. You say, well, how in the world am I going to convert that into a time? Well, we can use time, and we can use this really nice function called as.date. We'll put our time object in there. We'll tell it the origin is this thing. That's our origin, and our time zone is UTC. Okay, so now if we look at our time, look, it's actual real times, going all the way back to 1880-01-15, right? So here we've got every month that we've got here since 1880. So that's kind of cool. Okay, so let's now get our anomaly. Let's call this anom, ncvar_get. Let's go ahead and get the, remember it's called, what is it called again? If we look in our connection here, it's called temp anomaly. We can just copy and paste this thing. Temp anomaly. And the question is, do we want all of this? Do we want all of this? Remember, lat is, length of lat is 90, the length of lon is 180, and the length of time is 1,669. So if we actually requested all of this data at one time, it would be 90 times 180 times 1,669. We would be getting a lot of numbers back. You'd be getting 27 million numbers back loaded into our memory. That might slow our machine down a little bit, so we're not going to do that. So we're going to use an interesting function here that is called, or on the inside of f, we can add an argument called start, which is where do we want to start counting. This is going to be 3 numbers that are concatenated together that reference, let's just pull up f here again. We're looking at anomaly that reference these dimensions, lon, lat, and time. So I'm going to start with the first longitude, I'm going to start with the first latitude, I'm going to start with the first time, and I'm going to count. So I'm going to start there, and how many am I going to count? Well, I'm going to count, how many am I going to count? I'm going to count, it would be 90 to get all of them. I'm sorry, yeah, 90 longitudes. I take that back. Longitude size 180. I'm going to count 180. I'm going to count 90 to get all of them, and I just want the first layer. So that would be one way to get it. Or if you just want all of the entries in that dimension along latitude, you can just put in a -1, just like this. So this is saying, start at 1, give me all of them in the longitude direction. In the latitude direction, start at 1, give me all of them. Remember, this is referenced by long Latin time. Start at 1, give me the first one. So when we run Anomaly, the dimensions of Anomaly are now 180 by 90, and we can do an image.plot of lon lat anomaly, and this will give us what our temperature anomaly looked like in 1880. Let's go ahead and add a map to that. There it is. 1880, that's the temperature anomaly. Okay, that's nice, but what happens if we just don't want one layer, but we want a time series at a location? We want a time series at a location. Well, to do that, we're going to make two more objects called lat range. This is the range of latitudes that we want to get. So let's just pick them near the mid-Atlantic, 37 to 38, mid-Atlantic and the ocean. And long range equals concatenate -73 to -71. So that's going to be up in this area right in here. So what we're going to do is going to request a much smaller area, but we're going to drill down to all the times. So we're going to do lat range and long range, and then we're going to create these indexes. So our lat index is going to be a function that we call which. And we're going to ask which lat is greater than or equal to our lat range, our first element, and lat is less than or equal to lat range, our second element. So which of those is true? So we want to look in lat. So if we look at lat, there's our vector lat, and we're going to say which one is greater than or equal to lat range, the first element. Well, lat range, our first element is 37. Which ones are greater than those? Well, there they are right here, 37, greater than those. And which are less than equal to lat range 2? That's 38. Well, you know what? I'm just going to make this 39. I'll make that 39. Yeah, because these are 2-degree bins. So here's 37, here's 39. We should get these two numbers. So it's going to tell me which index that is. So if we look at this and we just run lat ind, this says 64. Whoops, let me run this again. This says the 64th and the 65th element of lat. So if we do lat, bracket lat ind, it's going to pull back 37 and 39, which is exactly what we asked for. So 37 and 39 are the 64th and 65th element in the lat vector. So keep that in mind, because we're going to use that vector indexing to pull data out of this NetCDF file. Let's do the same thing for long range. So we can do long, which long is greater than or equal to our long range, on, and on. All right. Long end. Okay, 54 and 55. So if we do long end, those are the longitudes that we requested, 73 to 71. Anything in there, it just happens to be those two. Okay, so let's now create an anomaly time series. We will use nc_open. We'll connect to connection F, and we'll use temp anomaly. We'll just edit this thing here. So we'll do a temp anomaly. We're going to start now. Where do we want to start? we don't want all of the all of the longitudes. We just want the longitude, our first index, which in this case was 54. So we want to go from, remember, if we look at F again, this thing has dimensions of ln, lat, and time. So ln end 1, that is going to be saying, I want you to start at the 54th element. We're going to do the same thing here. Lat end 1 is going to say, start at the 64th element for latitude. And what are we going to count here? We don't want all of them. We're going to count the length of ln end. Well, what is the length of ln end? Well, it's 2. So you're going to start there. Oops. The length of ln end is 2. So we're going to start there and count 2. Okay? All right. We're going to do the same thing here for latitude. No. One more time. Okay, this is going to be length of latitude end, and here's time. We're going to start one, but we want all of them now. We want to drill down in time. So this is going to be a big time series. I'm going to go ahead and run this thing. Oh, unexpected error. I probably had one too many quotes, or one too many. There we go. We shouldn't be using NC open. We should be using NC var underscore get. Okay, here we go. All right. So if we look at the dimensions of Anom TS, you'll see that's 2 by 2 by 1,669. So it's 2 ln wide, 2 lat, north-south, and has a length. So if we just do of 1669, do an image dot plot of TS a third, and it's just these 4 blocks, just those 4 blocks, 2 by 2. Okay, so here's what we're going to do now. Now we're going to take that and we're going to average those 4 blocks together for every time series, for every time period. So we're going to do nom ts, use a function called apply. And apply, we're going to apply to a nom ts 3 mean and na.rm equals true. Okay, so you notice the dimensions of this anomaly TS here. That has 3 dimensions, 1, 2, 3. So we could average everything together and just get one number for the entire time series. Or we can say, I want you to average across the longitudes, I want you to average across the latitudes, or average across the times. This is saying, this second argument here, which is really the margin argument, if you look at apply. Let's look at the apply function. See margin, vector indicating the subscripts which the function will be applied. Right? Another way to think about this is that we want to preserve the third dimension. We want to preserve time, and we want to average these other things together. So we can run this, and now the dimensions of anom ts are null, but the length of it, 1669, it's just one long time series. So let's just go ahead now and plot tm, our anomaly time series, just for this location. Type equals L. Plot. And there it is. There's our anomaly time series just in that location from 1880 to 2000. So you can pick out different areas to average over for this, but NetCDF is super powerful because you have access to these data sets that are gridded that are really big, and you can just subset what you want out of them.